Hi, I'm Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is a bug. Yesterday we started implementing pink noise and we did not finish because we had a bug. This is what the bug looks like. This is white noise, it's working. It's pink noise. And it clips to plus 26 and then it just stops. So today is debugging day. We'll figure this out. First thing you're going to notice is that I installed that Visual Studio Code extension to syntax highlight JS effects. Maybe that will make the stream nicer for you. Maybe it will make no difference. I don't think it helps me a lot because it's such a simple language with such simple syntactic rules, but it is what it is. So let's go to the pink noise section of the code and reread. In fact, I'm going to start on the demonstration part of it, because last time I was completely neglecting. I didn't even wire in the function calls for this part, and that was a bug. So I'm going to start with the use of pink noise. How do you use pink noise? Well, first of all, you need to have different pink noises for different channels. So you create an array, then you loop over the channels and you create an instance. Oh, this is a mistake, isn't it? Yes, this is already a mistake. I should be using memory, not arrays. In fact, that's something that I think I have noted already, and it is, yes, not something that I talked about on the stream, but it's something that bugs me. I think that we should have a notion of arrays that you can just simply index into instead of having to use our little .data kind of thing. Maybe we'll do that today if we can manage to fix this bug real quick. We'll see. So that's a mistake already. But I'm not sure it's the main one. Or in any case, you need to have multiple pink noises, one per channel, and you create instances of pink noises. In that channel, new pink noise. Same for brown noise. And the same bug was happening here, but I don't think that the brown noise was faulty, so go figure. Maybe because the brown noise is a simpler data structure, it's just a single field. Yeah, who knows? Right. And moving on. You mean, see, that already was something that I couldn't find yesterday. It's very hard when you spend the whole day just programming, and then you try to do a stream and you're trying to program some more. Keep that in mind. Sometimes it's useful to take a break. And you see how this is highlighting weirdly? I'm not sure I love this syntax highlighter. But I mean, it is a best effort basis, right? So it's not too bad. Right, so in the sample, we are going to check which type of noise we have. If it's white noise, we just generate that. If it's pink noise, we are going to find the instance of pink noise from this array. No, from this chunk of memory, so that's right. Then you pass that along and you generate a new sample. Same for the brown noise. And then you multiply that by the amplitude. And that's all right. That part I'm pretty sure works. So that's already a bug that we fixed. Let's go to the part where we implement pink noise. So we have this constant. Remember that the notion of pink noise that we are implementing, there are different ways of doing this. One way is to have a series of white noises and they are updating at different rates. One channel of white noise, I'm going to call it something else, not channel. One source of white noise is updated every sample. One source of white noise is updated every other sample. One source of white noise is updated every fourth sample, and every eighth sample, every 16th, 32. And if you add up all these sources of noise, that's pink noise. Because when you are updating the white noise in different rates, you are low pass filtering that source. And if you add everything up, it's going to have a slope that is almost 3 dB, indistinguishable for all our purposes. But I should note something that is actually kind of theoretical and interesting. Pink noise, as we discussed at length yesterday, is in between white and brown noise in terms of the spectrum. White noise has a 0 dB slope, brown noise has a 6 dB slope, and pink noise has a 3 dB slope. So it's in the middle. But it's not only that. The shape of the wave on the time domain is also in between. White noise looks completely crazy. Let me open the article again. So we are basing our implementation off of this article and some further developments on another website. But this picture here is showing that pink noise is the shape of the wave in the time domain is in between white noise, which is completely random, and brown noise, which is more correlated. It's in between. It's almost correlated, not quite. So, and when I say correlated, I just mean that subsequent samples depend on the previous ones. And it's also the case that pink noise is in between something completely random and something boring. So we can use white noise, we can use pink noise as noise. That's useful in many contexts, but we can also use this pink noise generator as a source of randomness. And we may use this randomness for something else. For instance, in this article, they are using it for selecting pitches. So you have this composition, this song, that is notes and durations selected using white noise. And if you just do that, it sounds just completely random. It's like a monkey playing the keyboard. And if you do it with brown noise, it sounds too boring. It's like you are playing scales. Can you show me the PDF, please? Thanks. It's like you're playing a scale. It's boring. But pink noise is in the middle. It is correlated enough to have sense and meaning, but it's not completely random either. It's interesting. It's not crazy. Just the right amount of variation that we think is interesting. So we could use this source of white noise in our library to do noise, but we could use this as part of a bigger plugin, selecting pitches, or maybe with a step sequencer kind of thing, we could have a random button, and this randomness could be based on pink noise. Cool stuff. So let's go over this implementation. It has this constant that we can change. Right now we have 5 sources of white noise that we are adding up. Actually 6, because we have a source of white noise that is always updating on every sample, then one every other sample, and so forth. And for the one that is updating every sample, we don't need to store it, so it's not here in the data structure. But then we have a pink noise data structure that has all these sources of white noise, and each of these sources is just one sample. It's just the white noise as it has been updated last time. Then we have a counter, and this counter is necessary to determine which of the sources of white noise we are going to update this time. There is a very nice graph of this over here showing how to select here. So if you think of the time as going from left to right and each source as one line, then this is the first source of white noise, this is the second source of white noise, and so forth. And the X represents when we need to update this source of white noise. So this is updating every other sample. Actually, this is a full graph. So one is updating every sample, one is updating every other sample, updating every 4th, 8th, 16th, 32 samples. So we need to store all these white noises, and we need this counter to determine which source of white noise we are going to update, which line has an X in it. And note that each column is only going to have at most one X if you discount this source of white noise that is always updating. It's not even in the data structure. Then we do need to store the previous output, because one of the advantages of doing the updates this way instead of this way, This is the original proposal in the article that we just had on the screen. But this is the version that is a development. And the nice thing about this one is that there is only one X at most in each column. So it means that we can store the previous sample that we output. We can subtract the old version of this and add the new version of this source of white noise, this little X. So before we update the source of white noise, we subtract the old one, we add the new one, and then this way we don't have to add up all these 5 different values. We can just subtract and add. So we cut from 5 additions down to 1 subtraction and 1 addition. Great little optimization. And it's a trick that comes up often. If you can come up with something called a difference equation for what you are doing. So in this case, we have sort of a difference equation in which the pink noise at sample I, or maybe sample n, where n is an index, is equal to the pink noise from one sample ago plus the white noises, I'm going to call these whites, at this should be index. I'm going to call this the magic index. That's the index of the line, so which source of white noise we need to update. So we subtract the old one and we add the new white noise sample. That's the difference equation determining how to go from one sample to the next. It's called a difference equation because it's the difference between samples. And if you can come up with something like this, typically that's going to be fast to use fewer operations, make things better generally. So that's why we are storing the previous output. Now, all of this may be subsumed by the fact that we are using memory and we are indexing into memory. We would have to measure, because I believe that maybe going to memory is more expensive than 5 additions. But never mind that, we are going into this. It's a trick that we also used when implementing RMS. Exactly the same story. So that's the data structure for pink noise. I'm going to put a new line here to differentiate pink noise and white noise and brown noise. They're different data structures, but they are all related to noise. So I'm just going to keep them all in this section. Or maybe I could group things differently. So I'm going to do a refactoring while I'm in the middle of debugging. That's never a good idea, by the way. You should never be refactoring while you are in the middle of fixing bugs. But here we are. I am grouping together things that are related to the initialization of pink and brown noise with the sections that are implementing pink and brown noise, which I think is a smart move. I think it's a good way of going about this. And then I do have to call these guys from there so that they will be called eventually when we initialize the library. Some good old function extraction, no big deal. Right, here we are. Now let's review the implementation of all the noises. Why not? I'll first commit what I have because I kind of like it. I'm feeling the itch to commit. So white noise is just a random number that's between 0 and 1, times 2, that's between 0 and 2, minus 1, that's between minus 1 and 1. Great. Then let's move down to brown noise because it's simpler. Brown noise is a data structure with a single field, which is the previous sample. Because there is a correlation, right? So we have to remember the previous sample and apply a small difference to get to the next one. Then to initialize a brown noise data structure, we create the data structure, we say that the previous sample is 0, and then we return it. Then to create noise, we get a hold of the previous sample, we generate the current sample, and we have this travel amount kind of thing. I think that this is sort of like an initialization kind of thing, and now that this is closer, I'm happy to do what I did with the pink noise and have the initialization setting here. Another refactoring while debugging. But there you go. This is a constant that is related to the brown noise generation. And the cool thing about doing it this way is that you could change this constant if you wanted. If you determine that this constant is bad, you can change it in the code. While it was here, it was a local variable, so you didn't have access to this. But now you do. It's kind of a private API sort of thing. You shouldn't be touching this, but now you can. For better or for worse. And I'm going to put a new line here just to separate the definition of the data structure from the definition of the constants. And I'm going to do something similar to the pink noise. Now, how does the brown noise work? First, I get a hold of the previous sample. And then we have this current sample situation here. I think I'm going to just call this sample. Just like that. Oh, I need to rename this one as well. So previous sample. Oh, Bo is here. Hey, Bo. Great to have you here. Hope you enjoyed this. I am debugging, I am refactoring, and I'm probably breaking things along the way. That's the game plan. So get a hold of the previous sample. Then, oh, let me know, Bo, how do you like the syntax highlighter? So to generate a new sample, we take the previous one and we do this. Now this is essentially doing white noise and scaling it down. Oh yeah, Bo. So Bo sent me this pink noise implementation that is using a different strategy, and that's interesting and all. It's actually called New Pink, and I don't know much about it, but it's not the implementation that we are using. So I'm not gonna borrow from that. But it's supposed to be better, faster, better, stronger. Yeah, I think there is somewhere, I forgot where I found that link. I think it was in Stack Overflow or something. There was a link to like, oh, I have this new implementation of pink noise using a different algorithm. I don't know exactly what's going on there, but I think it has to do with filtering white noise, which is more or less what we are doing. It's not too far from what we are doing. It's just a different way of reasoning about what we are doing. Same way as in this formula, how we were filtering white noise, or you can think of it as small movements of a particle, the more physical interpretation. Either interpretation is correct. It amounts to the same code even. Right, so let's use white noise and scale it down. And I think that even the number of operations is not going to change all that much. So this may be more explicit. Yeah. Bo is saying that there was a link in the email. Yeah, I'm aware of this other technique. In fact, in the implementation for brown noise in Audacity, remember how yesterday I brought up that the brown noise implementation in Audacity is using sort of a similar trick So talking about brown noise, and it has that constant that was exactly the same as the one we calibrated by hand. And they do have an implementation of pink noise, and check this out. It's filtering white noise. And I think that the new pink implementation is doing something similar to that, but then again, not familiar, so cannot really speak to that. Right, so we are just taking white noise and we are scaling it down by this travel amount kind of thing. And then we are folding it back onto itself, which is sort of interesting to look at how they are doing it here. They are not folding it back. They have this notion of leakage, so they're sort of filtering again. They're sort of filtering in such a way that it will be guaranteed to be between -1 and 1. But we are doing something different. We are folding. So if the sample is greater than 1, we fold it back into the -1 to 1 range, and if it's less than 1, we fold it back into the -1 to 1 range. Then we store it for later and return it. So that's brown noise. Let's review white noise, and then we'll see if all the changes I'm making have any resemblance of correctness. So for pink noise, I already talked about the data structure. So let's move on to how we create an instance of this data structure. We create this white noises array. And it is kind of silly to use an array in this context because we already have this size over there. So I'm just going to use memory instead. And then everywhere where I am using this data kind of thing, I need to remove it. Just like that. Right? The advantage of an array over a chunk of memory is that an array knows its own size, but we don't know its size. It's over there. In fact, we didn't ever use the size of the array. So using memory is going to save one slot in memory, and it's also going to be simpler. So white noises, chunk of memory with 5 slots. Then this is, oh, I just realized something. We'll get to that some other day. Right, okay, so moving forward, how do we make one of these data structures? We allocate a chunk of memory for the white noises, we start the counter at 0, and there is this previous output kind of thing. I think I'm gonna rename this to previous sample. Or even, because it's not the previous sample, there is a source of white noise that we are adding at the end. So it's not even the previous sample. It's white noises sum. That's what this is. And this counter is not really a counter. We are going to find a better name. So when refactoring, one of the biggest challenges is finding good names for things. And I think that this is not a counter. This is white noises index. Yeah. That's more or less what it is. It's not an index into the array, so calling it an index is sort of misleading. Let's look at the theory again real quick. To see if they have a name for this. Maybe this is already a term of art. No. So it's it's not really an index. It is more like a, I'm going to call this an update index, which is sort of a bad name, but at least it makes you think, oh, this is not an index. So what is an update index? Because remember, there is this whole logic of extracting the number of leading zeros from this number to actually get the index. So that's why I'm calling it update index. Great. Right. Okay, now this makes a lot of sense. I do like the names now. So we have the noise to generate a sample of pink noise. We get a hold of the white noises, the update index, and the sum. And then there is this index to update, update index and index to update, which is silly. I'll go with counter, whatever. So we have the white noises. It's a chunk of memory, so I can just directly fetch that. Then we do have the counter and the sum. Then a white sample. Well, I do like that name, yes. And then this index to update kind of thing could just be index, I suppose. Fair. And then we start counting the number of zeros, and we do have to quadruple check this logic because it is kind of a big deal. In fact, there are lots of discussions online on how to compute the number of leading zeros on a pattern of zeros and ones. And there are processor operations specifically for this. If you look at the operation codes that you can issue on an ARM, on a PowerPC processor, and even on x86 processors, there are operations, assembly operations just for that. Such a useful thing, apparently. And we don't have anything like that in JSFX, but we are coming up with our own thing. And we have to quadruple check this logic because it's so freaking complicated. And I bet there is a bug in here somewhere. So yeah, let's dive in right now. Feeling good about this. So we start at index 0. That would be this line here. And that's a silly way of doing this. But all right. While I take the counter, that's the thing that I want to check the number of leading zeros on. And to check that, I am going to AND, bitwise AND, with one left shifted 0 number of times. So I'm going to check the rightmost bit on this one. If the rightmost bit of the counter is 0, then 0 and 1 will be 0. So we need to go to the next one. And then we do this. On the other hand, if the rightmost bit of the counter is 1, 1 and 1 is not equal to 0, so we go to the next one. Or we stop the while loop. Go to the next line. Okay, all of that seems to hold. And then I am 1 off because I just found the index of the first one, right? This is the index of the first one, not the index, right? At this point where my cursor is, this is the index of the first one, and I want to know the number of leading zeros. So just subtract 1. Such a silly way of doing this. But I think it's necessary. Let me reflect on this for a moment. I will commit what I have, and I will start sketching some changes to this. No, this cannot be -1. So what I did right now was just shifting everything, the whole logic by 1, but then I could end up with a -1. Oh, okay, I think I got it. So if I start with 0 and I reverse this logic, then I think it works. Okay, so I start with 0. How many leading zeros do I have? 0. Now let me go and I will try to find a 1. No, this is not going to work. No, I think it needs to be 0. I'm going to keep counting zeros. So how many zeros do I have? 0. Then I don't need this +1. Okay, I'm back where I started because now I need to subtract 1 at the end. Yeah, I think that was the best way of writing this. I'm gonna pull the trigger and extract this. No, I'm gonna leave a to-do here. To-do, extract this into an auxiliary function. Or maybe even, I am trying to avoid having to-dos all over the code base because then I will never address them. So, see, I don't have any to-dos in the code base. Great. So I'll just make note here. Extract from ping noise an auxiliary function to count the number of leading zeros. And why do I even subtract this at the end? Because I could just have a 0 and that would be fine. I think that's a mistake. I mean, look at the amount of time I'm spending to implement the number of leading zeros check. 4 lines. And there are all these discussions on how to make this fast and all these sorts of tricks with bits. Trying to do it the simple way with just a loop, and already so hard for me. Okay, I think this is correct now. That line was a bug, I think. Should not be removing 1 from the index. Because if I have no leading zeros, I will start with a 0 and then I would end up with -1. And that would not make us happy. Then we do the trick where I said that the difference equation, where the sum is the previous sum minus the... Yeah, I'm gonna do it this way. It's a difference equation, so better read as one, right? It is minus the white noises at the index we calculated based on the number of zeros, leading zeros, plus the white sample. The difference equation right there. Then we increment the counter and we check if the counter is equal to, then we do this bit shift. Well, I just said bit shift, didn't I? YouTube is gonna think that I'm saying something else, but I am doing a bit shift. That's exactly what I'm doing here. So I'm not sure I got this range right, but I think I did because I counted things yesterday and it seemed correct. So if that's the case, then I wrap the counter back to 0. Yeah, I'm going to review this experimentally later. Then in this last section, I'm just storing stuff. So let's go over this one more time. In that particular index, I am updating with the new white sample that I've got. Then the counter is updated. And then the sum is updated. And then we return the sum plus a constant source of white noise that is updating every sample. Great stuff. So we reread all the code. Now, can we run this code and look at it? Let's do that. Naturally, before the stream, everything has been muted, okay? So no surprises. Okay, white noise is working. Brown noise is working. Looks like brown noise. Let's have everything on the screen at once, simultaneously. Well, I don't really like how I laid this out because I wanted the spectrum analyzer to have a bit more range to work, so yeah, I'll put the funky wave behind me. How about that? So let's start with white noise again. White noise, a slope of 0, flat line, really, really jumpy, very random looking. Different for every channel. Importantly, we do see green and pink, and they are not the same. So different sources of white noise for different channels. Great. Let's do brown. So now brown has a slope of 6 dB, flat line. Well, if you look at it, I mean, it's not perfect. You can sort of see something here. It's not awesome. It's not the best. It is something. It's not too bad either. Then if we hold this for a moment, it starts to look like the graph on that paper. Great stuff. Now for the moment of truth, let's go to pink. And something is super slow and jumpy. Let's put a slope of 3 on this guy. And this looks like pink noise to me. It looks about in between in terms of randomness. This line is almost straight. I do see some comb filtering here. But the main issue is that, look at this, the CPU is through the roof. So I think that we implemented pink noise. There is something terribly slow about the way we did it. And this kind of logic kind of reminds me of let me stop this, by the way. It may be even affecting the performance of the stream. This kind of logic that we have with the counter wrapping and everything kind of reminds me of the initial implementation of our filters, the RBJ filters. In the initial implementation of the RBJ filters, we had the coefficients and the previous samples that you have to store as memory chunks. Just like this memory chunk. And that was too slow. And then we realized that the fix for that was to store the samples not with an array or a memory chunk, but just store them directly in the data structure. I was trying to avoid doing that. I thought we would be able to get away with this time, but apparently not. Let's go over this and look at the variables to see if they make sense. But maybe what we are going to do next time we meet is try to make this fast, because I think it's now correct. It looked correct. It looked kind of okay-ish. Not too good, not too bad. What do I want to look at? Well, I think I can look at I think I want to look at sample.noise. So this value is behaving in a way that makes sense, and if I switch to brown noise, then it should not be oscillating as fast, and it kind of stays in the same region for a little while. This is clipping. Oh, I know an issue. This is clipping. So the clip I know how to fix real quick. We are adding 5 sources of white noise. Well, actually 6 sources of white noise. That will make values go between -6 and 6. So we need to scale the white noise as we generate it. And maybe the best place to do it is here. Maybe there is a faster way, or not a faster way, but a nicer, maybe there is a place where I can do this that will save some operations. But for now, I will do it real slow and divide by... I'm gonna make things worse in terms of performance now, I think. But I will divide by this number of sources of noise plus 1, because that's this source of noise, and now the value should not clip anymore. Full compile reset. Let's switch to pink and make it louder. And look at this, see if it clips. No, it doesn't clip anymore. Great. I have an idea to try and understand what the heck is going on in terms of performance. Let's remove everything we have going on here. Let's draw an item that is 6 seconds long. Drop our effect there, put some pink noise, make it louder, and glue it. Now this has no reason to be this slow. How about we make it a little bit shorter? Why is this so slow? Now, because we are gluing, there is no problem of the frame drops that we saw before. And if I loop this, and put a slope of 3, then there you go. It's not, as I said, perfect pink noise. This strategy was not going to give us perfect pink noise, but I do see some dips, especially this in this range. So it's not perfect, but it's probably good enough for most purposes. But it is super, super slow. So there you go. I think I proved that we implemented pink noise using the strategy mentioned before, adding sources of white noise, different generators of white noise. We implemented the thing and it works, but it's super slow. So next time we are going to try to figure out why. And I bet that one possible solution is to just hard code this number by having 5 numbers here, 5 places, 5 variables, the same way we did with the filter. But then the question is, why is this so slow? It's accessing just one more place in memory. I mean, the counter is a place in memory, the sum is a place in memory. And this is just another place in memory. Why would that be so slow? Same with the filter, really. I'm not really sure I understand why that is so slow. Is this the time where everything is going to break and we will have to resort to pseudo objects? I don't know. We'll figure it out. So the schedule is on Monday. I may be streaming here, finding out this pink noise performance issue, or I may be streaming with Arya. It all depends on whether he gets better. You will know because here on YouTube there will be a video or a stream scheduled on his channel or on my channel. I don't know. Let's all hope that Arya survives and gets better. So yeah, and have a great weekend. And thank you everyone for being here. I see you back on Monday, either here to continue the pink noise or on Arya's channel to do some delay and to work with rotations on a plane and everything. Lots of fun stuff. All right, bye. Have a good weekend.